I'm Chao from UT Austin, and today I'm here to tell you about Callas, a distributed database system that offers unmodified transactional application the opportunity to achieve a level of concurrency that can currently only be reached by rewriting all part of the application to explicitly handle concurrency. In essence, Callas unlocks the untapped performance potential of ACID paradigm without sacrificing its generality and simplicity. Indeed, generality and simplicity are at the core of the appeal of transaction abstraction. Let's face it. It is nice to know that I only need to wrap my code into a transaction to get a guarantee that it will be executed atomically, isolated from all other transactions, and its effect will be durable. It is nice to know that when reasoning about the correctness of my code, I only need to verify each individual transaction transitions the database from a consistent state to another consistent state without worrying about the internal logic of other transactions. Yes, ACID is nice, but can we afford it? Our community has been struggling with this problem for at least a decade. The ACID paradigm simplified development by making transaction easy to compose building blocks, but the rub is isolation. Enforcing isolation limits available concurrency and greatly reduces performance in the presence of contention. We have then come to believe that low performance is the price one has to pay for the simplicity of ACID paradigm. The NoSQL-based movement has responded by trading simplicity for performance, but at a heavy cost in complexity. There have been several attempts try to find the sweet spot between ACID and base, including our saw paper in last year's OSDI. But though the complexity reduced, it is still non-trivial. No matter how carefully one trades, the simple truth is that for many applications, when it comes to the ease of programming, outside of ACID, there's little sweetness. The only question is how sour it is going to get. Then, the proposition that motivates Callas is simple. Instead of trying to draw performance from weakening the abstraction, embrace it. Guarantee ACID's properties uniformly with no ifs and buts, and focus instead on finding a more efficient way to implement the abstraction. The architecture of Callas is based on a key observation. While ease of programming requires ACID property to hold uniformly across all transactions, when it comes to the mechanism used to enforce these properties, uniformity can actually hinder performance. To put it differently, any one-size-fits-all concurrency control mechanism designed to work correctly for all possible pairs of transactions, whether based on locks or optimistic concurrency control, will necessarily have to make conservative assumptions, passing up opportunities for optimization. Callas then decouple the concern of abstraction and implementation. It offers ACID properties uniformly to all transactions, but use a novel technique, modular concurrency control, to customize the mechanism. MCC makes it possible to think modularly about the enforcement of isolation. It gives Callas the flexibility to partition transactions into different groups, assign each group a specialized concurrency control mechanism, and guarantee that as long as in-group concurrency control mechanism provide isolation within each group, the isolation will also hold among transactions across different groups. Fundamentally, MCC allows Callas to leverage the principle of separation of concern. When considering the correctness and performance within each group, Callas only need to worry about the transaction that live in this group, rather than all possible transactions that someone may possibly write. This modular thinking is of course crucial to simplify reasoning about correctness, but it is crucial to extract a great performance. Because of the limited scope, in-group concurrency control mechanism can seek opportunities for concurrency with unprecedented aggressiveness. In the rest of the talk, I will discuss how we implement MCC and leverage it for great performance. I will first discuss Nexus lock, the mechanism that makes modular concurrency control possible. by regulating the conflicts among transactions that belong to different groups. Then, I will discuss in detail this in-group concurrency control mechanism, and I will introduce a new technique called runtime pipelining. Next, I will discuss something that may already cross your mind. How does one assign transactions to groups? Finally, I will put all these threads together by discussing the performance of Callas. Before I start in earnest, let me introduce the theoretical foundation that Callas is based upon. Here, we rely on the beautiful work of Adia, Liskov, and O'Neill, who provide the elegant and rigorous way to define isolation. For simplicity, please let me only focus on the main constraint, preventing dependency cycles. The main constructor for detecting isolation violation is the direct serialization graph. The nodes of the graph are committed transactions, and the dependency between two transactions is represented as the direct edges between them. In this execution, for example, T2 reads object A before T1 writes to that object. We say T2 depends on T1, and there's a direct edges from T1 to T2. Similarly, T1 writes object B after T2 does, creating a dependency cycle. For serializability to hold, no such cycle should exist in this graph. Come back to our context. To establish the correctness in MCC, we need to guarantee there is no dependency cycle among any subset of transactions, whether they are in the same group or belongs to different groups. We can actually split this problem into two steps. First, we need to avoid any dependency cycle inside of group. Then we need to also prevent the dependency cycle that among different groups. Let me start by focusing on the second part of the problem. Assume we have in-group concurrency control mechanism that avoid dependency cycle within each group already. All we need to do is to establish a mechanism that avoid dependency cycle that span multiple groups. To that end, we introduce nexus locks. Nexus locks are used to regulate the behavior among transactions that belong to different transactions, belong to different groups. Nexus locks are ubiquitous. Every transaction that reads or writes any data object in a database needs to acquire a nexus lock on that data object. To avoid affecting the concurrency within each group, nexus locks have a dual nature. When two transactions from different groups try to access the same data object, a nexus lock functions like a normal lock. Only one transaction is allowed to access the data unless they are both reading it. The other one needs to wait. If, however, these two transactions are from the same group, nexus lock allows both of them to proceed, leaving the enforcement of isolation to the in-group concurrency control mechanism. Unfortunately, simply acquiring nexus lock is not sufficient to prevent circularity. Consider the following example. Initially, T1 from group 1 writes object A, so it grabs nexus lock on object A. Before it finishes, another transaction from the same group writes A. As I mentioned, nexus lock allows two transactions from the same group to access the data concurrently. This creates a dependency from T1 to T2. Let's say T2 further writes object B and commits. After that, a third transaction of group 2 comes and tries to write B. It can certainly do so since no one is holding nexus lock. This creates a dependency from T2 to T3. Finally, T3 writes object C and commits, and T1 writes object C. Now T1 depends on T3, creating a dependency cycle. Notice that this execution does not have dependency cycle within either group 1 or group 2. Nevertheless, a dependency cycle that spans all three transactions can be still formed, violating isolation. What's wrong in this example then? To answer this question, let's go back to see how traditional locking avoids dependency cycle. With traditional locking, the dependent relation is actually tied to complete before relation. If T2 depends on T1, T2 cannot start until T1 finishes. Similarly, T3 cannot start until T2 finishes. Since completes before is inherently acyclic, by tying these two relations together, traditional locking guarantee the depend down will also be acyclic. Coming back to our example, what is wrong is now clear. Next lock tie depend down to completes before only for the transaction not among different groups. And it does so on purpose. Imposing the same requirement to the transaction within the same group will severely limit in-group concurrency. The key to solve this problem is to observe that while completes before is sufficient to prevent circularity, it is not necessary. Callas then refined this condition. Rather than tying depend down to completes before, Callas binds it to the weaker releases locks before. Specifically, Callas imposed the requirement on the order in which nexus locks are released. If T2 depends on T1 and they are from the same group, T2 cannot release its nexus lock until T1 does. Come back to our example. This refinement does not require T1 and T2 to execute sequentially, but lets them to execute concurrently. The nexus lock release order requires T2 to hold its nexus lock until T1 releases its own. And this is enough to prevent T1 from becoming dependent on T3. We have seen how nexus lock enable modularity of MCC. Next, I'm going to show that this modularity, the ability to partition transactions into different groups and apply separate and potentially different concurrency control mechanisms inside of each group, is crucial to the performance of Callas. The intuition is simple. The aggressive techniques with strong assumptions may not be effective when applied to all transactions. They can be effective for a small set of transactions. One example is runtime pipelining, a new in-group concurrency control mechanism we introduced that allow Callas to leverage the untapped performance potential. But let me start with the observation that by limiting scope, grouping can bring new life into mature techniques. Consider, for example, the case of transaction chopping, a 20-year-old technique used in recent systems such as Linux and the DRTM. To increase concurrency, this technique uses static analysis to identify the finest chopping that continue to guarantee serializability. When it works, transaction chopping delivers better performance with no additional programming effort from the developers. Unfortunately, it does not work as often as one would hope. The problem is that for chopping to be safe, the pieces it generated should not be involved in what is called an assay cycle. Imagine connecting the pieces that belong to the same transaction with an S-edge and connecting the pieces of different transactions that may potentially conflict with an C-edge. If a cycle with both S and C edge is detected, the offending pieces must be merged until the cycle is removed. This prevents independent cycle from forming at runtime, but also reduces the concurrency. Unfortunately, it is actually very easy for assay cycle to arise when one needs to consider all transactions. Grouping can make transaction chopping more effective by limiting the requirement of no assay cycle only to the transactions within the same group, resulting in a final chopping. As we will see later in our evaluation, our experience confirmed that grouping can help transaction chopping, but only to a limited extent. The problem is that sometimes the finest safe chopping allowed by this technique is still too coarse to produce significant performance benefit. An extreme but quite common case of this phenomenon occurs when a transaction cannot aggressively chop because it may conflict with other instances of itself executing concurrently. Consider this example. There are two instances of the same type of transaction, which try to write three objects, X, Y, and Z. Transaction chopping cannot help here because the only way to avoid assay cycle is to not chop at all. Callas solved this problem through a new concurrency control mechanism called runtime pipelining. which leverage the runtime information to achieve final chopping and great performance. Consider again our example. Assume we still chop the transaction into 3 pieces, and suppose that a dependency is generated between first pieces of these 2 instances. The key observation is that all we need to do to avoid dependency cycle is to ensure that any future conflict between these 2 transactions are resolved in the same way. That is, the dependency can only go from the left to the right. Runtime information actually can turn C edges, which originally have no direction, to a directed edge. As long as all these edges point in the same direction, there can be no cycle. We can then use the runtime mechanism to pipeline the execution of these 2 instances. As soon as the left one finishes one piece, the right one can start with it. Detecting dependency at runtime has another advantage. Rather than taking the pessimistic view of static analysis, in which 2 pieces must be considered as conflicting if they potentially touch the same data object, we can declare a conflict only if they actually touch the same data object at runtime. This can significantly reduce the need for even invoking runtime pipelining. In our paper, we show how to generalize the intuition behind this example. Runtime pipelining actually requires C edges to not cross. In this paper, we describe a simple algorithm that can take a situation like this, in which C edges cross, and there exists a semantic dependency between pieces within the same transaction, and transform it into this, ready for runtime pipelining. This new algorithm, instead of rejecting all choppings that generate assay cycle, allow more aggressive chopping that involves assay cycle, but only of the kind that can be broken through runtime pipelining. This combination of more permissive static analysis and runtime checks allow Callas to find novel opportunities for concurrent execution. Before we move to the evaluation, let me address a question you may have. How does one group transactions? Before we move, it is actually easier than you might think. The reason is that identifying, the reason is that identifying the best grouping really only matters for those transactions whose high conflict rate bottlenecks the application. These are the transactions that can benefit most from aggressive concurrency control mechanism. As we noted in our short paper last year, the Pareto principle teaches us that these transactions are few. The rest can be put in a single large group using a standard concurrency control mechanism, such as two-phase locking with negligible performance impact. In principle, we can then exhaustively explore the optimal grouping for the few remaining transactions. The paper discusses an iterative greedy algorithm that approximates this ideal. Now to evaluation. Today, I will only talk about the end-to-end performance of Callas. For the extensive evaluation of the role that different components of Callas play on its performance, I refer you to the paper. We run our experiment on cloud cluster using a configuration of 10 shards with 3 replicas each. We evaluate Callas using a set of micro benchmarks and 3 workloads, the TPC-C benchmark and 2 real applications, Fusion Ticket, an online ticket selling application, and front accounting, an open source accounting program. For brevity, I will only focus on the end-to-end performance of TPC-C and Fusion Ticket. Let me walk you through this graph. First of all, notice that the throughput of Callas for TPC-C is 8.2 times that of MySQL Cluster, the assay code base from which our prototype descends. With Fusion Ticket, the ratio is 6.7 times. The performance improvement is achieved without any modification to the application code. So where does this performance benefit come from? To get a better idea, we also measure the performance of applying standard transaction chopping to the same workload. We find that transaction chopping yields some benefit of TPC-C, but none at all for Fusion Ticket. If we apply modular concurrency control and use transaction chopping within each group, we achieve better performance in both applications. In Fusion Ticket, in particular, the benefit is quite large, because grouping allows transaction chopping to focus on a small set of transactions. It leads to few assay cycles and great concurrency. Replacing transaction chopping with our runtime pipelining as the in-group concurrency control mechanism solves the problem of self-conflicts. And as you can see, performance really suits up. Finally, we compare our throughput with SALT, the system that we presented last year at OSDI. SALT weakened the ACID guarantee and required developer to manually rewrite a few performance-critical transactions to increase performance. What is really nice is that Callas, without requiring any modification to the application and without weakening ACID, stay with 5% of SALT's performance. There has been a lot of work on improving the performance and the scalability of ACID transactions. Some prior work has focused on improving performance only for a certain type of transaction, such as read-only or partition local transactions. Callas instead tries to identify conditions to improve performance that apply to the entire workload. These conditions are in general hard to establish, and as we have seen for transaction chopping, MCC can help by requiring this condition to only hold within each group, rather than globally. SDD1 deserves special mention, since like Callas rely on the notion of transaction groups, which in SDD1 are called classes. Classes in SDD1 and groups in Callas, however, have a very different purpose. SDD1 uses static analysis to identify conflicts between classes rather than transactions, and leverage the observation that transactions assigned at runtime to different classes can conflict only if their classes conflict. In Callas, transaction groups are the key to separation of concerns. By delimiting the scope of each in-group concurrency control mechanism, they allow them to find new opportunities for concurrency. To conclude, Callas leveraged two classic principles of system design: separating concerns and decoupling abstraction from mechanism. To make a strong case for ACID application can be fast. The key is modular concurrency control, which enables specialized concurrency control mechanisms, such as runtime pipelining, to aggressively pursue new opportunities for concurrency. Thank you.
Atoladia, Google. So I was wondering if you considered defining your correctness condition for intergroup concurrency control without using a locking definition? And did you consider, for example, an optimistic concurrency control mechanism? Because one of the things I found, which was a bit disturbing when the correctness condition for isolation levels were defined, they were defined in terms of short locks and long locks. So your condition is also in terms of locks.
Yes, we actually we think about it very carefully, and we think it will work, but we never really implement this grouping on top of OCC or MCC, and it's really interesting work we are exploring right now.
Okay, thanks.
Chao from New York University. My question is, how would you expect your core protocol to behave in an environment with much faster network connections, such as RDMA, or even faster inter-processor connection?
I think there's faster. The hardware is faster and faster, but as long as the contention is still bottleneck, I think it's worthwhile to explore the aggressive concurrency control mechanism.